Welcome everyone. This is Dan Pitt here again, and organizer of panels, invited speakers, along with Alan and Benjamin and Oscar Hernandez. And I'm just here to welcome the panel. And the panel chair is once again Scott Schweitzer, who did it last year. And I can't think of a better person to introduce this subject than Scott. I mean, I think of two just sort of different things. One is sort of performance art, and the other is accelerators. Well, performance art, Scott is the performance artist and everything he's done. And suddenly accelerators came on the scene a few years ago to augment, processors, storage, and networking, especially in a data center, a new category of devices. Well, Scott has been an accelerator really from day one, whether it's with CPUs, with interconnect technologies. He has driven this stuff. He's got the personality that makes it hard to say no to. And so he was, made his initial mark at NEC and really in the server market. He was at Miracom, and we used to have a pretty good presence from Miracom and that whole scene in hot interconnects, 10 years ago. 15 years ago. And he was tremendously effective at getting their stuff accepted, and the whole views accepted in the market. And then, he joined SolarFlare, and they were acquired by Xilinx. He was a mover and shaker there. Glad we have Xilinx on the panel. And then he was just snarfed up by Achronix. So, and he's pulled together this whole topic and the panelists and set it up as a von Neumann versus programmable logic, which we sort of touched on last year, but he's taken it to a further degree this year by asking the question, which is the dead end? And I can't wait to hear what the panelists say. And if only John von Neumann could be here to see that we're still using his name in vain this way, frankly, I think he'd be excited and thrilled to do it. So it's my pleasure to introduce the panel chair, Scott Schweitzer, and I'll let you take it from here, Scott.
Thanks, Dan, I appreciate that. Today we got 6 panelists, 3 from the CPU side of the house that have used ARM and so forth and their SmartNIC implementations, and then 3 from the FPGA side of the house. So what I'll do is I'll introduce each one of them, and then they'll have about a minute or so to position themselves and their company in the space. And then after we've gone through all of those guys, we'll jump into questions. I've got 18 prepared, and then I'm keeping an eye on the Slack channel, and as that stuff is appropriate, I'll slot those in. So let's do it in kind of an alphabetical order. So Cary, Ussery is the first guy on the panel. Cary has been with Marvell Semiconductor for the past decade and is currently the VP of Software and Support for Infrastructure Processors. And with over 20 plus years in the semiconductor and embedded software market, including digital signal processors, advanced media processing solutions, DSPs, and microprocessor firmware, Cary is an experienced high technology manager, executive engineer, and designer. Welcome, Cary.
Thank you very much. I recognize some of that stuff as me. So I appreciate the opportunity to speak in the panel. I might like to start that, we believe at Marvell that acceleration of functionality for different workloads is very important, and SmartNIC is one application of that. I'm not sure I would have chosen the von Neumann word. So, I think there's a lot that's being talked about in the market now from data processing unit. And I think that's where there's some contrast together with FPGAs. And we are certainly in that camp. So anyway, looking forward to the discussion. I think it'll be interesting.
Thanks, Gary. Appreciate that. Next up, we have Mario Baldi. Mario is, this is Pensando's second year on the panel, and Mario is new to the group. So thanks for joining us today, Mario. Mario is a distinguished engineer or distinguished technologist, at Pensando, and he started with them 2 years ago. He has an exceptional understanding of computer networking and comprehensive knowledge of a broad range of protocols and technologies, a profound appreciation for Ethernet, bridging, and layer 2 switching, layer 3 routing protocols, network and transport layers of the TCP protocol stack, including various other protocols. Mario, thank you for joining us today.
Thank you. Sounded like a job application, but thank you. Yes, I'm with Pensando, and Pensando has developed a distributed services platform on which we offer networking services, security services, storage services, and observability services. And as the name says, the idea is that the platform is distributed. So all of these services are executed on what we called a DSC, Distributed Services Card, that is plugged into hosts, and it has Ethernet interfaces. So from this point of view, it's, you can call it a SmartNIC. Again, we like the term distributed services card, but at the end, we have this host adapter. And as many of, I guess, the architectures we are going to talk about today, it has some of, again, what this panel is called von Neumann's components, but also other type of components. So I think the strength of this card is integrating all of these components to achieve the performance that we need today on SmartNICs, which is pretty astonishing, and do it with the form factor and the power constraints that SmartNICs have. So yeah, so I think it's definitely important to to discuss what's the best, or what are the best architectural solutions for SmartNICs. It's very crucial.
Thank you, Mario. Next up is Michael Kagan. Michael is back for his second year on the panel. Thanks, Michael. As Chief Technology Officer at NVIDIA, Michael arrived at NVIDIA through the acquisition of Mellanox just over a year ago. Michael is one of the co-founders of Mellanox over 2 decades ago, and before that, he was at Intel as their chief architect. So Michael's been directly involved in shaping the history of networking. Michael, thank you.
Yeah, thank you for having me. So yeah, we are at NVIDIA. In NVIDIA, what we believe that data center is actually the new computer, and SmartNICs and or DPU, it's actually the platform to run the operating system of this new unit of computing. One Neumann machine is probably awkward name for this. It's not one Neumann machine. It's a platform to run the operating system in the distributed way, which is pretty much resonates with what Mario said. And that's what we are doing. That's my job at NVIDIA, to move forward and drive this vision. Looking forward.
Thank you, Michael. Now we're going to shift to the guys on the FPGA side of the house. Jim Dworkin. Jim and I first met in 2018 as partners, where at the time he was director of the cloud business unit and led the Xilinx acquisition of SolarFlare. Jim is a senior leader in the semiconductor industry who has carved out a broad career path, including engineering, architecture, applications, market, and business development, solutions architecture, and marketing roles. Today, Jim is the Senior Director of Cloud and Enterprise Data Center Business Unit at Intel PSG. Jim, it's a pleasure to have you join us today.
Thanks. Thank you for inviting me. Great pleasure to be here. And yes, I'm here on Team FPGA, and but I'm really here, representing, as we say, one Intel. So Intel is a much bigger organization than just PSG, which was the former company Altera. We are the global leader, Intel, in SmartNIC and what we call IPU deployments, thanks to the over 1 million units shipped into the Microsoft Azure data centers, but we also have multiple hyperscale cloud and other cloud and networking comms providers that are deploying our silicon in various types, FPGA, foundational NIC, SoCs, into these former SmartNIC applications, and some of them are IPU. So here at Intel, even though I'm representing Team FPGA on this panel, we bring the scale view here that says, maybe I'll give away the ending, is that I don't know that there is a winner, Scott. And I think the ultimate winner is going to be the customer, and the customer's ability to choose between multiple architecture types in order to build their infrastructure solutions. And I'll just end with this, von Neumann, as I was dusting off my old, very old textbooks. It's just so funny and ironic to me that the von Neumann architecture itself had its own inherent limitation in the single bus kind of structure for the fetch, decode, execute, kind of structure. And that problem got solved relatively quickly. And here we are, look at how advanced we are 60, 70 years later, and solving still IO, compute, storage, memory bottlenecks. Anyway, very happy to be here again. Thanks, Scott.
Thanks, Jim. And I think you're right. The customer is the one that ultimately wins because we're all competing to get their dollar, and we're putting our best technology forward. With that, we got Nick Ilyadis. Nick has extensive expertise in 5G, data centers, wireless infrastructure, AI, IoT, and connected vehicles. Nick was previously the VP of Portfolio and Technology Strategy at Marvell and Group CTO at Dworkin. Currently, Nick is the Senior Director of Product Planning at Achronix Semiconductor, where he's working on next generation FPGA solutions. And also, for full disclosure, Nick's my boss. But that doesn't mean I'll be tossing him some softballs today. So with that, Nick, thank you for participating today.
Thank you, Scott. Thank you, everybody. It's interesting to be on this panel because I've actually worked for Marvell and other companies here, so it's an old home day kind of thing. FPGA technology, Achronix is the upstart in the FPGA market. We develop high-end FPGAs with our current device, the Speedster 1500, has 1.6 terabits of Ethernet connectivity, dual PCIe Gen 5 interfaces. We have a 20 terabit 2D NOC that allows you to interconnect lots of logic inside of the FPGA in a very efficient and high-speed manner. And we are currently sampling our device to our customers and looking to go into full production really soon. So we're new to this game, but we're coming in strong.
Thanks, Nick. And finally, we have Rip Sohan. Rip and I also work together. We go back to January 2018 when he joined the Solarflare CTO group as an architect. Before that, he's held posts in academia and engineering and has consulted in the networking field for the last 12 years. Today, Rip is on the architecture staff of the Xilinx Data Center Group, where he's focused on SmartNICs. Rip, thank you for making time to join us today.
Thank you, Scott. And thank you for that maybe a bit too generous introduction. So just to put this into context, I work as part of the data center group, and the data center group acquired Solarflare, of which I used to be a part of. So the basic idea on our end is that we believe, like a lot of the other panelists, that there is no one architecture that will win them all. So being very customer facing, we are of the opinion, give everybody everything and let's make it work well. The idea behind our approach is that we want you to be able to not only use the data path or of a SmartNIC as it's provided, but augment it and change it as you will. And in response to applications which often come out of nowhere and where you'll want acceleration at kind of very short notice. So the traditional ASIC cycle is not fast enough to respond to this. So to that end, we're advocating an approach in which you have hardened accelerator blocks that make up the standard acceleration that you would expect to come out of a NIC, so things like LRO or a match action engine. You augment that with a bunch of cores where you can run traditional applications. And finally, the icing on the cake is you have FPGA fabric logic on which you can use to augment these existing processing planes or replace them, right, depending on what you want to do. Now, this is no good if you can't program it. So a large portion of our effort in the last 2 years has been spent on reducing the barrier to entry for people from the software field to make use of all the primitives we are providing. And I look forward to the discussion. Thank you.
Thank you, Rip. I appreciate that. Okay, so as everybody can see, we've got probably over a century of combined networking and technology experience on the panel. I'm going to pop the questions to everybody. They'll have about a minute to answer them. Also, I'm going to keep an eye on Slack. So if stuff comes up on Slack and it's good and it fits the discussion, I'll pop it in where appropriate. So listen for that. We're going to have a kind of a fixed lineup as we go through the questions. Cary will go first, followed by Jim, then Mario, Nick, Michael, and Rip. And then what we'll do is we'll move head to tail So that way we're rotating who's the first guy for each question with each question. So hopefully that doesn't confuse people too much, but I'll keep everybody kind of focused, hopefully. So moving forward and getting into it. Cary, you're up first, buddy. Packets entering or leaving the NIC will need to be queued before processing. Should this queuing be done on chip or off chip memory, or I should say in on chip or off chip memory? And if it's off chip memory, then what might be the appropriate type of memory, and how much memory might you want to have given the speed of the network and the number of ports that you have? So, Cary?
Well, thanks for starting off with such an easy question, Scott.
Sorry.
I think like a lot of things that you're going to hear today, the question is more nuanced and workload focused. So I don't think there's a situation where all the traffic can be and flows can be managed on chip that ends up being disruptive if you're in an environment that's, especially in an edge deployment or in a cloud deployment where you have millions of flows that you're trying to manage at a single time. Having said that, you don't want it all off chip because the bandwidth and latency for accessing is going to create significant bottlenecks in your performance to achieve the types of data rates that most people are looking at these days. So I do think you'll see a hybrid approach of on chip and off chip, some very intelligent caching of what stays on chip. I think there's a secondary effect where how much of the packet data is bundled together. So we feel significantly that the move towards batch packet processing is a big shift in the industry and has changed the way that you build the data paths internally. So, technologies like VPP have really changed the landscape a little of how the software operates on it. And like Rip, I'm a vice president of software, so I believe the software angle is probably the most important angle and not the hardware. But I think I did my minute there.
There you go. How about you, Jim? What are your thoughts on queuing?
Yeah, largely agree with what I heard, and I hate to drag out the "it depends" argument, but let me give you a flavor for kind of how we look at this and how I've seen it in the various companies I've worked at to solve these problems. So we've seen densities of flow rates and virtualization and number of flows driving the number of queues needed, anywhere from the thousands to the millions. So that's a hard thing to, these investments are high in these solutions. So it's a hard thing to solve for, to try to figure out where most of the market lands. But those are the type of considerations one goes through when you come up and plan a solution to bring out to market for how much on-chip versus off-chip memory. So it's really about, to me, looking at the use cases, as Cary said, and looking specifically at the temporal locality of the packets in those flows that you want to support. And that gets to a couple of different directions, like how tightly coupled do you have a compute engine there to take the initial flows to set up the flows, and then you want your fast path to be able to handle the density of flows that you want. So there are two different vectors there. Any given flow, like an elephant flow, can have lots of small packets or a very high packet rate just for that one flow. And then you want things really on chip. And then you could have a very diverse environment where you have not a lot of temporal locality, a lot of mice flows. And so you basically tune an architecture to that. And so what we favor here is balanced architectures that are scalable on both ends of the spectrum. And that being from control plane to data plane, you need to have a good balance for the applications. And look, I'm team FPGA, so I'm going to be here to say that with the FPGA and the fast path, that gives you the most flexibility to react to changing conditions and use cases, because the market does change. That's the one constant.
Gotcha. Mario, how about Pensando? What's Pensando's thoughts or your thoughts? Mario?
You're muted, Mario.
Sorry, guys. I was saying that I'm going to tell you mostly my opinion more than Pensando, though if I think of it, Pensando's architecture is following more or less this concept, which is that, you know, it seems to me that today at the edge, SmartNICs need to work at line rate. They should not have to queue packets because they cannot process them, and consequently, you may have queues. You need to have queues because you still need to prioritize, and you might have to absorb some uncertainties in the processing delay, but processing time. But I don't think you should need extremely deep queues. So in this sense, most queuing should be on chip. But there's obviously another kind of storage of packets that you need to do, which is when you need to wait for more packets, when you need to work at the message level, and you need to put packets together into messages to then process them further. And so in this case, you may want to use off-chip memory because you will need larger amount of memory. And you know, the trade-off here is that hopefully only a fraction of your traffic is going to need this kind of message level processing. So most of the traffic hopefully is going to be handled wire speed, only buffered on chip, and then a certain amount of traffic that's processed usually at a higher level, a higher protocol level. That one you want to put it off chip. You need to still have a lot of memory bandwidth, but it's going to be less than to sustain their line rate.
Nick, what are your thoughts on this?
Yeah, for Team FPGA. So being that we're developing FPGAs and our customers have very different use cases. I mean, our FPGA can be used from 10 gigabits all the way up to 400 gigabits. I don't think I can get the amount of memory right on chip. Right? I want to give my customer the ability to tune their system performance, their system capacity based upon external memory. Today, you know, in terms of high-speed memory, there are really two types of memory that can address this. There's the HBM, which is basically a co-packaged memory with interposer technology, or in the case of what Achronix uses, which is GDDR6, where that is the graphics memory. And with GDDR6, it's external. At least our device has several channels, so you can populate as much bandwidth or as much capacity as you need for that particular application. So coming from an FPGA, malleable architecture that our customer can develop into different types of use cases, being able to support an external memory to give them that flexibility, that depth, that performance that they need for their particular application, I believe is the best path forward for us.
Okay. Michael, what do you think about this?
Well, in terms of networking, there are really two types of data that you need to process. The data itself, the packets that are coming or being sent, and some control information that is needed to do something useful. So actually, I agree with Pensando, with Mario, that you shouldn't keep queues on the chip for the data. When you want to send the data is up there in memory, and you know, you just, when you read it, you just send it out. And when data comes in, you need to be able to drive it to the destination pretty much at line rate. The other part, and you need to design your NIC in a way that is balanced in terms of host bandwidth versus network bandwidth. The other part is the control structures that you need to have in order to process it. And here again, you do need to have a caches, and we are at Mellanox in old days, we developed quite a lot of very sophisticated caching of the control information. But it's a matter of more of the memory bandwidth than the memory itself, we use host memory for pretty much everything on our simple NICs, and we use the attached memory DDR on the DPUs to keep the context, and we just need to balance, to tune the design so the bandwidth meets the requirements. And now, when you go higher up to the stack, when you need, as Mario said, you need actually to create a message or to put together the structure that is coming in. It's actually a different type of data processing. It is more like memory to memory. So yes, when you go higher up on the stack in the DPUs, you have layer 7 and maybe even up, sort of total applications running. And here it's the design of the data processing machine, balance the memory bandwidths and the caches with the execution required. So my take is that on chip, you only need to have caches and shortest queues as short as possible.
Gotcha. Rip, you get to say the final word on this one, buddy. What do you think?
I think there's very little I can say that hasn't been said. So I agree with a lot of the panelists that you want to keep your on-chip memory, especially your expensive memory, as small as possible. You want to cut through where you can. There's definitely a case for having slower, a larger capacity memory. And in most systems, you're going to see a tiered memory layer. So where you have a very high speed, expensive SRAM, maybe slightly less expensive, more capacity DRAM, and then maybe you spill over to host memory. One thing I will point out, though, is that just to broaden this out a little bit, it's not only just about the amount of memory you have. You're only as good as the primitives you have for classification and moving your packets around, right? So that's a big thing that I think a lot of people don't pay attention to, or that hasn't traditionally been an issue in the industry, and that's something we need to get smarter at as an industry. So how do I quickly work out what goes where, sort it, and send it on its way in a way that is efficient and that allows me to make complete use of all the resources I have? That's still a little bit of an open problem in some areas.
Boy, it's almost as if you're reading my questions here. So, Jim, you're first up on deck this time. Once packets are obviously queued up, they need to be classified before they can be acted upon. Should the classification and the action itself actually happen in hard logic, soft logic, or be done in a CPU or GPU, and why? And let's try and keep answers a little bit tighter to a minute, guys.
Okay, so thanks for that. Team FPGA says this. So when you use a CPU, I mean, you can get the job done with either one, but for us, the optimum on the FPGA side here is to run that logic in reconfigurable hardware. And the reason to do that is that when in any CPU architecture, these days you have caches, L1, L2, sometimes L3 and DDR. So you end up with latency, long tail latencies potentially. You end up with, depending again on that temporal locality of those packets, you can get really bad latency effects. And that's why pure SoC-based solutions don't tend to meet all the customer requirements at the high end. Okay, so that's the quick answer to your question, Scott.
Mario?
Yeah, I mean, I agree with the fact that it should not be fixed logic. I mean, requirements are they change over time, so it should definitely not be fixed. Our approach is to use application-specific processors. So at the end of the story, you're going to decide what should happen with your packets when you process those packets. You go through the protocol layers, you see the information you need, you look at state information you have, and you decide what you should happen with the packet. Then the queuing system should be simple, should just have multiple queues and queuing policies that could be configurable among a set of different policies, scheduling policies. But the decision of which one should be applied is, my opinion, a programmable decision, and we use software on application-specific processors.
Gotcha. Nick, your thoughts?
Sorry, just finding that unmute button. Yeah, I believe that we want to provide the maximum flexibility to the user or the implementer of the SmartNIC to be able to parse and do classification on pretty much any field that they wish. And of course, as we know, protocols keep evolving. Fields get defined for different packets, or you want to go deeper into the packet and look at the upper layers. Having the flexibility of being able to do it in FPGA by just changing the hardware programming, really gives the customer, the end user, or even the developer of SmartNIC the most flexibility and able to achieve that.
Okay. How about Michael?
Oh, okay. First of all, I do agree that you can't do these things on the CPU, and you need to design your chip in a way that you most of the traffic hits the fast path that you designed for. Once you have enough experience in the design of the networking, you can have accelerators and basically services that you can chain using the CPU. And this CPU is actually kicked in the sort of slow path on the exception when you need flexibility that you didn't predict. But the key thing is to be able to design the chip that on one hand that is effective in terms of ASIC implementation. On the other hand, you leave yourself enough flexibility to tune and adjust the functionality and performance as required. So far we have been able to do it. We have CPUs. Actually, from our very first chip, we had embedded processors that were doing the job in terms of making these accelerators work right. And the art is to have right flexibility on one hand and right accelerations on the other hand. And at the end of the day, networking is not something which is absolutely unpredictable and unknown. There's enough
Gotcha.
experience that you can do. Yeah.
Rip, how does the Xilinx FPGA crowd weigh in on this?
Again, kind of broadly in agreement, right? So think about it this way, right? Your most expensive resource or your most precious resource is your CPU. So you want to make sure that by the time your data hits your CPU, you've done as much of the pre-work, if you will, that you need, or all of the pre-work that you can, so that the CPU just does the thing it's good at and that it's supposed to do. What that means for us is that it's almost like you have a hierarchy of routing logic, right? So you'll have your hard function that maybe will do your coarse-grained, very high speed and maybe 200 or 400 gigs routing. Then you may have FPGA logic, which does some sort of application level classification. Now, I hesitate to point out that that can be expensive, right? So it can cost you a lot of resources, but it can be done, and it can be hard to get right. And then once you've done all of that, you want to make sure that what you send to your CPU is kind of pre-classified, pre-computed, and all it does is do the actual function it needs to do, whether that's compression or lookup or whatever it is. So I think there's a place for everything. And again, it's a bit of a waffle answer, but I think unless there's a specific application, you can't really tell. It'll depend on the application itself. HFT trader will have a very different classification methodology from somebody doing big data analytics, for example.
Okay. And Cary, you get the last word on this one, buddy.
Sure. So, in some ways, I think this will happen a lot. I agree with what a lot of the panelists are saying, but let me draw some distinctions. One is, I think, absolutely, you don't want to do classification on a general purpose CPU. I don't think anyone in the market does that, and no one thinks it's a good idea. Well, some people do it. So having said that, you're with whether it certainly shouldn't be hard-coded logic because there's a lot of flexibility required in the market now. Protocols are changing, headers are changing, different overlay networks exist. So you need something that is flexible and programmable. So maybe where there's a distinction between the von Neumann viewpoint and the FPGA viewpoint is that from my perspective, that flexibility needs to exist on a minute by minute basis and not on a configuration of a product. So you need to be able to support, different programmability that can be downloaded onto a card quickly in a matter of minutes, not something that's fixed ahead of time.
Okay.
But not CPUs. Micro-coded engines are good.
Yep, gotcha. Thanks, Cary. Okay, so Mario, you're going to kick this one off. So with queuing and classification and actually acting on packets, all happening, within the SmartNIC or DPU ASIC chip, however you want to view it. This drives up the demand, obviously, for on-chip network bandwidth, right? Which is always a challenge. How do you shovel the stuff around? So, what is your approach to on-chip networking, and how is it going to adapt to meet the increased demands of, beyond 100 gigabit Ethernet? Mario?
Yeah, well, obviously you need to have architectures that can cope with it. So you cannot just use your out-of-the-box solution. The architecture has to be, I believe, has to be hierarchical. You cannot have, again, it depends on your architecture, but what I'm seeing around architectures with a lot of components. So you cannot possibly have all components talking to all components. You'll have a hierarchy. You will need probably to have some caches that need to be coherent. So the design of the network on chip is not trivial. You'll probably have more than one, and they have to be adapted to your specific application. And I think this has a huge impact on the performance of your DPU. As I wrote in blogs and in white papers, I believe that here the key is really how you put together the various components, how tightly and well you integrate them. And also, I believe Pensando did a quite good job in that. But I'm sure also others, I just know much better, obviously, the Pensando architecture. But that's definitely a key aspect.
Nick, how do you weigh in on this?
Sorry, I keep finding that mute button. But I think that flexibility is that interconnect flexibility is very important, and how you tie those pieces together. Again, being an FPGA, we are malleable. We let our customer configure their architecture the way they want, and we want to have the most flexible interconnect and subsystem flexibility that you can to allow your customer the degrees of freedom they need to achieve their goals and performance. So I think that's very important here. And in the case of Achronix, we have a 2D NOC that is finely tuned for that exact purpose.
Okay. Michael, what?
Yeah.
How Bluetooth, Bluefield use this? Bluetooth.
Well, on-chip networks, it's topic on its own. On the NIC, it is or smart NIC, it is a different challenge than on the switches. And the way you implement it is you basically know what flows you're going to support and figure out how to change the accelerators that you have there. So I think, and it's actually, when you do it in the ASIC, it's I believe it's much more straightforward than doing it FPGAs, because then you just place your components at the right places. And as Mario mentioned, you have the right caching and right buffering structure. So that's one of the key things to have a successful product.
Gotcha. Rip, what's your perspective on this?
Again, I think everything that I would have said has been said. I'll just make the point that so Mary made this interesting point of a hierarchical structure, right? And the fact that you kind of assume that as line rates go up and clock speeds go up, that you're going to have to replicate more of the same components. We very much buy into that approach, right? And what we kind of aim to do with our architecture is to make sure that we can move data around fast. So, I mean, you know, we find that 50% of the time that applications are spending are spent just moving data around, and then about 50% is actually compute. So the idea is make it easy to move data faster when things need to take a step up. Make sure that the core logic provides that. And then from our perspective, where the challenge lies is, can we scale the way people write applications to scale up in their data processing rate? So kind of writing an application at 10 gig is completely different from the way you would write it at 100 gig. Kind of the basic structure is the same, but the trade-offs in terms of optimization and how you get this thing to actually run can differ quite a lot. So I think the point I'm trying to get across is that it's not just about the hardware itself, but it's also about the software. And the way you structure the software will very much influence how the hardware is designed.
Excellent. Well, Cary, Rip seems like he teed that one up for you.
Yeah,
The
I'm
software.
liking Rip's software perspective. It's good. Yeah, I would agree with, you know, I guess Mario started it, that it's not, there's not like an on-chip network. There's a lot of optimized, call them sub-networks, that are used in different aspects, at least from an SoC DPU perspective. So, you know, how you might put together, for instance, an optimized subsystem for L1 processing and 5G with a bunch of possibly DSPs and hardware accelerators and maybe a crossbar switch is very different than your mesh or your fabric for putting together CPUs, which is different from your flow processing. So maybe hierarchical, maybe just heterogeneous is how the network really looks in the chips. And I think one of the advantages you have taking an SoC DPU type of approach is that getting those networks optimized and right is really difficult. So when I hear someone say, we love the flexibility, our customers can do it, you have much more sophisticated customers than I normally come across, because really that's an expectation we have from the customers, that we figured out how to get the optimization of data running around in the network so they can focus on their actual value added in the software.
Gotcha. Okay, well, Jim, you get the final word to say on network on chip. What are your thoughts?
Yeah, thanks, Scott. Try to be brief here. So I'd like to answer this in kind of two steps. And the first step leads in with the customer view. And, you know, if you're going to go out and buy a car, you don't necessarily ask the vendor, how large is the hose, the fuel line going from the tank to the engine? So we're talking about building Ferrari type, you know, Tesla type vehicles that can go fast at 200 gig, 400 gig, 800 gig. And so it's our job as a team here, well, both sides, both teams here, to build solutions and to offer solutions to our partners and our customers downstream that they can get their job done and get their objectives met. So that's the mindset we come from. And I just would like to respectfully, you know, remind the audience of our position that the strongest vendors in the market are going to be the ones that offer the most choice, the most flexibility. And this is important in such a nascent market as SmartNIC, as IPU, when there's a lot of fragmentation out there, and they're expected to remain that way for a while. Now, working with our customers that I mentioned earlier, the hyperscalers and the next tier, especially in the cloud for my business, we have worked very hard in co-design partnership with them to tune and balance the architectural solutions that that they have taken to market for their own data centers. And then we've taken those solutions where they buy our chips and they build their own, and we have created a platform, initially SmartNIC, and it's an IPU platform that pairs the Xeon D processor with the SoC with the FPGA from our team, and it's balanced. So we look at the balance between the PCIe attached to the tightly coupled SoC. We look at obviously the Ethernet line and the host connect, and make sure that all of those things are impedance matched so that ultimately the car will drive as fast as it's supposed to. So whether you choose that or we harden certain functions like crypto as an example, that's a pretty common one that you see hardened. And with that tightly coupled hardened data path, now you've released a lot of the pressure internally on some data paths there that lead to a more tuned and balanced architecture. So I could probably go on and on about that, but hopefully you all see the gist.
Well, you actually just teed me up for the next question without even knowing it. Nick, balancing what we can do versus what we should do in hard logic versus programmable logic or GPUs or whatever. And I want this to be a short answer question, not a minute, but like what 3 DPU functions do you feel should be in hard logic versus some sort of programmable logic?
Yeah, I mean, obviously things like Ethernet interfaces, PCIe interfaces, standardized functions should be hardened, right? You don't want to waste precious FPGA real estate on well-known protocol engines or whatever the case would be. Also, things like potentially lookup memories, TCAMs, things that are used for searches, those should be optimized on chips to allow faster lookups and things like that. What else could be hardened that would make sense would be maybe what?
You only need 3.
I need 3. Okay, I got 3.
You got 3? Let's move on to Mike. Or unless you have something else.
Oh no, maybe some sort of parser that you can have a hybrid FPGA packet header parser type of hardware. What else do you want?
Michael, how about you?
Well, you need to have a right classification engine and hardware. You need to have things like basic data processing, like cryptography, compression, DMA. Classification must be programmable, but it needs to be, really fast. That's already 4.
Okay. Rip, what are your top 3?
Again, assuming DMA, PCIe, etc., are all hard for application functionality, I would say packet classification, especially kind of at the L3, L4, crypto for sure, both the storage and the networking functions, and basic packet processing. So this is things like LRO, checksum insert, checksum verification. Those 3 are a must-have.
Gotcha. Cary?
It's gonna be hard not to copy people. Certainly crypto, certainly both the crypto side as well as the security side, like IPsec. I think let me try to add something a little different, which is work scheduling. I think scheduling work across multiple components inside the chip.
Okay. And finally, Jim.
Yeah, I agree, Cary. It's going last. It's hard to come up with something new there, but not just like DMAs, but data movers. So on-chip data movers, efficient, maybe something like compression in certain use cases. And if you're going to do RDMA, like iWarp and a TOE, or Rocky queues, hardened queues, and the congestion control logic, those are valuable to get hardened.
Boy, oh boy, you just teeing Michael up for the next question. Michael, now that we're thinking about 400 gig Ethernet, beyond that, how do you intend to scale your architecture? More cores, more hard logic, some programmable logic, and this isn't just for Michael. Obviously, it's going to rotate for everybody. But what are your thoughts for how do you actually heat more stuff on to get to 400 gig?
Well, 400 gig is, for us, it's a little bit history. We are now working on the 800 gig. But the way to scale, you scale vertically, and we have been doing the scalability for last, since we started Mellanox. And you actually go both ways, both vertically and horizontally. Horizontally in terms of that you take advantage of concurrency, and vertically you just do things that you used to be, configurable, programmable. You just learn how to do it hardware. So we managed to double the performance, not just the wire rate, but also higher level performance every 2 to 3 years by factor of 2. And again, it's concurrency and more sophisticated data processing.
Got it. Rip, what about you guys? You just throw more gates in there? What are you going to do?
So it's kind of, it's pretty standard, right? So increase bus widths, increase line rates, take your most commonly implemented soft logic functions and harden them so they can run faster, and they're available to everyone. Add increased parsing and classification functionality, so being able to do more fine-grained parsing and classification. What we also are finding is that whether you like it or not, you're probably going to be adding more cores, right? Because more line rates means more software running on the onboard CPUs. So you're going to need more cores to do that.
Gotcha. Cary, what are your thoughts?
I sort of like the term Jim used before, data movers, because that's an important part of getting those line rates, is how to optimize the subnetworks of where data is being operated on, and harden how data gets moved between the pieces of that subnetwork. And I think it's diversification of that network is an important piece of achieving data rates. And what I mean by that is, isolating where data needs to move and not trying to generalize it so that any data can move to any specialized compute or accelerator on the chip.
Gotcha. Jim, your thoughts?
Yeah, the things we work on are packaging technologies, and we try to keep our solutions efficient and as low power as we can. So the power for the performance per watt is still in a deployable envelope, especially not only in the core, but all the way out to the edge. A couple other concepts. Number one is software. So important just to get that kind of easy for customers to move between different solution types as they have different deployment types, be it at the core to the edge, or a cloud data center to public cloud to hybrid to on-prem. So we are investing heavily. Obviously we're going to do a lot of the scaling techniques that were talked about by the other panelists. I happen to believe that the architectures that we have, some that are public and some not quite, but I believe that those solution types are scalable, and that's what we think about. And I'm not sure, I don't mean to throw down here, but I'm not sure, having worked at different companies in the past that have different solutions that match the ones that some of the panelists have, I'm not sure that those solutions are scalable to get to the 400 gig, 800 gig and above without suffering from degradation, nonlinear effects. So, microcode was mentioned earlier. That's always been something I like to stay away from. But anyway, my point is that we're working on different, vectors of how to scale from packaging to CPU choice to FPGA density and hardened logic in order to create the solution.
Okay. Mario, what are your three things that should be in hard logic?
Yeah, so there are a couple that were already mentioned. So I skipped though, although I think they are important. But actually, I'm going to connect to one that Jim said, which is software. And that's definitely something to keep in mind. I mean, all these devices are programmable, and that's one place where usually there is some improvement to implement. Along the line of software are tools, like your compiler can make a huge difference. And the third one, I would put the overall architecture. Again, the way all the components are integrated is really crucial in achieving highest performance.
Okay. Nick, you get the final word on this one, buddy.
The question was on the 400 gig, right?
Yeah, it was.
Yeah.
It was.
Okay, you asked Mario about the three things, so I wasn't sure.
Yeah.
What
What are the three things?
yeah, so 400 gig. I mean, today the Achronix device with our 2D knock is actually very capable of doing 400 gig. Is actually able to actually scale all the way to 1.6 terabits. So I believe not just having, in the case of FPGA logic, just having FPGA logic, but having this, high-speed network on chip that allows you to move data between parallel processing blocks and pipeline processing blocks, allows you to scale up the system to accommodate these higher data rates. Now, in terms of where these things get used inside of servers, you're going to have potentially, hundreds, thousands of flows simultaneously. So not only is it the speed of the interfaces, but it's how well you can do traffic management, load balancing, and shaping. So I think those all go along with just the raw speed of the device. And those are attributes that the Fpga technology, I feel, has the capability to be able to do at line rate.
Okay. Okay. So next question, Rip. The ARM acquisition is, still in flux, but it may actually close one of these days soon. Most of the partners here, Xilinx included, use ARM for control plane stuff and other things, even data plane, cores within their SmartNIC architectures. Are you or others considering other processor architectures? I know, for example, Intel has, x86 bolted onto one of their SmartNICs, but are they considering other architectures like RISC-V or something else?
Okay, so I'll start by prefacing this as this is a RIP opinion, not a Xilinx opinion. And
thank you.
Then I'll make the next point, which is you may have heard of two big companies merging, one of which is a three-letter acronym, and the other which is Xilinx. So I cannot speak openly, but it's not untoward to think that we may be thinking about other architectures and other kinds of processors. Beyond that, I will say one thing. So kind of the whole ARM versus RISC-V versus other things. So yes, so I mean, we commonly do look at other architectures, right? I mean, we looked at RISC-V, we will look at RISC-V again, but there are a few things that kind of need to be borne. One is that you're only as good as the software that you can run on your processor, and that's where I think ARM has done a really good job. Intel's done a really good job. You've got the compilers, you've got the linkers, you've got the operating systems, you've got the people maintaining them, you've got the Ubuntu the Linux distributions, Ubuntu or otherwise. And I mean, processors are difficult to do, but there are many of them. I think when you take the whole kind of thing in an ecosystem, at an ecosystem perspective, you only kind of end up with 2 or 3 options, right? So kind of technically many options. From a business and kind of holistic perspective, it usually falls down to at least 2 or 3 if you have that. Again, waffly answer, but that's what you'll get out of me.
Cary, what do you think?
Again, this will be my opinion, not Marvell. So,
of course, that's what I expect for this question for everybody.
I'd say a few things. One is, I don't think that the CPU architecture is the main issue facing customer satisfaction with DPUs or SmartNICs. It has much more to do with all the other topics we've been talking about today and not so much with the CPU architecture. Having said that, ARM has been extremely innovative and successful and extremely well supported architecture with an ecosystem, as x86. I think the NVIDIA has been an extremely innovative company and has done a good job to help push the industry forward. So I don't think there's concern about having to adopt different architectures for different reasons. Of course, having said that, like everyone here, we always evaluate everything and try to pay attention. I think if the RISC-V is a specific issue, I think for a certain class of processors, it's an option now, but that class of processors is not the type of CPUs we're talking about here today.
Jim, what are your thoughts?
I think it depends on what persona you're talking to. If it's a builder of equipment around, an OEM, I guess you would say, or someone building SmartNICs based on our platforms, then the choice of CPU becomes relevant to them, more relevant than an end user who would like a more turnkey solution. Although what that ends up at the end of the day is going to be really interesting, how it all plays from tools like P4 to stacks and development kits all the way up through the orchestration layers of the data center of the future. How are these things actually going to be used? How are microservices going to be run and distributed and executed at scale for the largest customers initially? So to some extent, the more you start thinking about those things, the less you start thinking about the underlying CPU technology or even FPGA that is underpinning your IPU. So I don't mean to sidestep the question. And by the way, I thought, Rip, your answer was quite good. I didn't find it waffly at all. And I'll go lean into the answer that says choice. Customer choice is important. And if you're building solutions based on our chips, our platforms, then working with a vendor that can make those trade-offs depending on the use case, on the market, on the bandwidth requirements, that's going to be the most important thing than any particular spot choice of one CPU architecture, Scott.
Gotcha. Thanks, Jim. Mario?
Yeah, I mean, I cannot do much more than echoing what Rip said. I mean, obviously, always every time you start with a new generation, you look around, let's say, and you have to look at the whole picture. And to all of the things that Rip mentioned, and I fully agree, I would just add that you look also at the various tools that are available to enable you to integrate that particular architecture into your ASIC. The various IP that are available around that particular processor architecture.
Right. Gotcha. Nick, what are your thoughts on this?
We are living in an open source world. And today, all the CPUs that are available other than RISC-V are obviously controlled by one or two entities. So I believe that having an open source, open architecture offering out there is as powerful because it will drive innovation and create a lot of different choices and competition too, right? So I think it's a goodness that we have RISC-V as an alternative. If you want something that's tried and true and well supported, I think maybe getting it from a licensee like ARM is a good choice. But if you're interested in new applications, new types of systems and cores that can be scaled from IoT scale to potentially even server scale, I think RISC-V gives you that opportunity and creates a potential ecosystem of suppliers for both the cores themselves as well as the enabling IP around them. So, I think it's going to create new opportunities. And as an FPGA supplier, some of those may end up as soft cores inside of FPGA. People can experiment with different instruction extensions. So.
Gotcha. Thank you. Michael, I know it has to be totally personal opinion for you because this is like right in the middle of your court.
Yeah, well, that's it. There's a few factors that you need to consider. One is the availability / cost of particular core, particular architecture, the ecosystem in terms of how wide do you want to use it, whether it's sort of for limited deployment or for you want to open it up for everybody. And last but not least, you sometimes want a CPU with the microarchitecture that's tuned for your needs. So you're basically between the ARM or RISC-V.
Gotcha. Okay, well, that's good. Cary, chiplets are getting a lot of attention these days. That's probably going to be the wave of the future. So given the high demand by SmartNICs for extensive on-chip functionality, memory, networking, et cetera, how do you see chiplets fitting into the future of your architectural plans?
Sure. So chiplets are the wave of the future.
I don't know.
That assumption. I think, chiplets are a very interesting technology to enable some modularity for companies like Marvell to create products for customers. However, one of the things I probably should have brought up in getting to 400G, a lot of the requirement to get, a lot of how you'll get there is going to the latest process technology. So, I think chiplets are one option for modularizing an architecture and potentially reusing and putting together different products for customers. But from a customer perspective, they don't really care.
Right.
So I would say it's really an internal discussion of when it makes sense or when it doesn't make sense. There are latency issues between chiplets, and we could go into arguments about chiplets versus full die, but
sure. Okay. Jim, your thoughts?
Yeah, the modularity is obviously most valuable in a nascent market where it's fragmented and you need to create different solutions and different t-shirt sizes, as you might say. So we certainly have that here at Intel PSG, and that allows us to pair up different fabric sizes with different IO, and it also decouples you from the obviously, I guess, from the individual underlying technology. So IOs can change, like CXL is evolving, and PCI generations are evolving, obviously SerDes. So what we need to get faster. I think the industry, the world is trying to move faster and faster, and the cloud computing market is the one that's driving a near annual now cadence of innovation. And it's amazing to me. And what used to be a 3-year kind of cycle that fit semi-nicely into the semiconductor cycle economics and dynamics is now getting squeezed harder and harder and harder. So, and at the same time, going into the most advanced technology nodes is getting so expensive that only the highest scale companies or the best funded can get into those. So the cost of doing these chips is so high, and the cost of getting it wrong is so high. So those are the factors I think that drive. But agree with I think it was Cary's point that sometimes you need to go monolithic, and to get highest, maybe ultimate performance and cost power trade-offs, you see those types of solutions at high scale. Those end up fragmenting the market even further because they might not be the right ones, the right t-shirt size for every customer.
Gotcha. Mario, what's Pensando's position on chiplets?
Yeah, well, it's mine.
Or your position?
Yeah, no, I mean, everything I could say was said already. I mean, in SmartNICs today, we have a constant requirement for more and more performance, and at the same time, lower and lower power. Not lower, but power is a major constraint, and cost is a major constraint. So at the end of the story, I'm not sure that chiplets are the right way to go for SmartNICs in particular, for SmartNICs that have to operate at the speeds that we see today.
Understood. Okay. Nick?
Yeah, so I think chiplets, as Jim was alluding to, does allow a company, semiconductor company, to create different flavors of their product offerings. Also allows them to adapt to new standards, and because these standards are coming fast and furious these days. So I think that provides that flexibility. I don't think it's a panacea. I think there's still going to be challenges with packaging and cost, yield, things like that. Once you dig into it and get under the hood and start looking at the specifics, it's not really Lego blocks. There's a lot of things that have to be taken into consideration. And I know there's companies like Google that are trying to create a chiplet marketplace. I think that's it's an interesting idea, though. I think the devil's in the details of how exactly to pull that off. So yeah, I think chiplets can be used by semiconductor manufacturers to create product variants and product families. I don't think that chiplets as a business that can be sold is going to be there for a while yet.
Gotcha. Michael, that Bluefield and Bluefield X-Die must be getting pretty big. What are your thoughts on chiplets?
Well, in general, I think we are moving toward having multi-die solutions. It is not a new one. We had this MCMs, but now there's new technologies that like 3D stacking that you can put actually multiple dies on top of each other. HBM already doing. You can call it chiplets. Another drive for chiplets is once we need to drive optics from the package, we'll probably need to be able to connect at very high speed, very short distance, different process technologies. So I think pretty soon we'll get chiplets pretty much everywhere.
Gotcha. Rip, your thoughts?
So I've got kind of two thoughts, and I'll talk about them both. So at kind of at a basic level, I think chiplets are really interesting because they allow, like other people have said, different configurations to happen. So maybe you want a device with 2 DPUs, or maybe you want 4 DPUs, and you can connect them in this weird and funky way that's specific to your application. And what it means is that the cycle is much shorter to get you that. So in that way, win-win, modulo the amount of money it's going to cost to do that. Kind of what excites me on a personal level is I think chiplets, especially where they're mixing and matching kind of higher geometry parts with lower geometry parts, is it's got this potential to open up an ecosystem, allow people who would otherwise find it really hard to participate in creating IP that can be used and that is slightly different or is slightly experimental or is coming out of a university and is only able to do 10 gigs. That's really hard right now, and I think where I kind of find it really exciting is that this will be possible, assuming we get the standards and everything else that kind of supports this right.
Gotcha. Thanks. Okay, we're going to shift gears from hardware to software. Jim, with VMware's Project Monterey burst onto the scene about this time last year. And last week, it actually went into early access. 4 of the panelists are Project Monterey partners on the panel. And just curious as to what your thoughts are on how it's going. Does it appear to be fulfilling its mission? For those folks that are not a partner, what are your thoughts? And are you positioning yourself against Monterey or just trying to get into Monterey? So we'll start with you, Jim.
Okay. Probably not a whole lot I can say there at a detail level. We certainly wouldn't position ourselves against Project Monterey. VMware is one of Intel's strongest partners and will continue to be, as far as I can tell. And so Project Monterey is quite interesting, and I think there's a lot of really interesting and challenging work ahead of us to kind of match up what I have been kind of talking about this whole time on this panel in terms of optionality and different architecture types and different solution types and platforms and chips in order to get the most out of our partnership with VMware on Monterey. So I don't think I can comment any more than that, but we absolutely find it quite interesting and look forward to that future.
Understood. Mario, Pensando was one of the key players in Monterey, correct?
Yeah, and I mean, I think the idea of Monterey is a great one, and it's in a way it's a confirmation of SmartNICs of the fact that they are really positioned uniquely in the overall architecture of the cloud and of systems today, and moving the hypervisor or some of its features to the SmartNIC is definitely very valuable for the SmartNIC world, but also for the cloud providers for the users of the hypervisors that at that point have this host CPU all for their customers or for their applications. I think I'm really excited about it.
Okay. Nick, what are your thoughts on Monterey?
Well, I think the the fact that the SmartNIC is being promoted now to be much more of a processing element or GPU, whatever you want to call the entity. For many years we've tried to promote offloading in the NIC, and I think standardizing that and creating a use model that cuts across multiple types of hybrid clouds, I think is going to actually enable more SmartNIC sales. So I think it's a good thing to try to create a standardized or open implementation of this that people can rally around. So I think it's a good thing.
Got it. Michael, you guys were a real driving force in Monterey. What are your thoughts?
That's right. I mean, VMware is sort of the data center operating system, and the right place to run operating system is on the DPUs. So it's very natural. Of course, we support it, and we work with VMware, and we, it's the relations we started, many years ago, yet in Mellanox, and we keep moving forward.
Okay, Rip, your thoughts?
Again, a Rip opinion. So I don't have a lot of observability what's happening at the business level with Monterey because I don't follow that, but I will talk on a personal level. Monterey does excite me. So it basically brings the same sorts of economies of scale in terms of data processing that you see in the cloud to localized data centers or any machine that is running ESX. What that means, I think, for customers that are in this audience is that it allows them an alternative to just going into the cloud and using these specialized systems there. Now, where I think it'll be really interesting from a technical perspective is to see, because we have these kind of localized versions of offloads happening, what comes up at the local level that then gets fed back into the cloud. I think that will be pretty interesting to see.
Okay. Cary, you get the last word on this one.
Sure. So I think VMware is a very important part of the ecosystem around DPUs and SmartNICs. I'd say, so we think they're an important partner moving forward, et cetera. I would say that part of our perspective is we see a shift from a traditional SmartNIC use case, which is really offloading networking between virtual machines and containers, to more of what we would call workload acceleration, where you're taking full workloads like virtual firewalls or a virtual DU in a 5G RAN situation. And when you start looking at those, you see gaps in standardization and missing pieces in the ecosystem. So VMware fits one of those, but discovery of capabilities for specific workloads in a cluster of resources allocated in the edge is another gap. Standard APIs for doing service chaining with containers. So I think Project Monterey is important, but it's only a piece of a larger puzzle that needs to be solved.
Gotcha. Okay, for the hardware guys, Mario, standards are important. So the development of both CXL and C6 are poised to change the face of how we view PCIe moving forward. How might one of these protocols, or maybe even both, fit into your future SmartNIC plans? And if so, which one are you going to pick, or which one do you think you'll pick? And what do you expect to be a dominant use case for either CXL or C6 in your platform?
Yeah, let me preface my answer with the fact that I'm not a hardware guy. So
I'm just going on rotation, dude.
No, that's right. My understanding is that the main driver for these technologies, these two technologies, is really creating a tighter bond, enabling a more efficient sharing and communication, mostly, for example, of memory. So I think that in a way, one of the value that we see in the SmartNIC is that, as I was saying before, it's quite uniquely positioned. It's there, it's part of the host. It is seeing all of the traffic that's going in and out, and it has a brain by itself. So I think that's how we position our distributed service card. That's an ideal place to use for security reasons. And so, for example, what we do at Pensando, we create what we call a hard gap between the host and the SmartNIC. So we sort of keep them separate so that the SmartNIC can be a secure environment that can protect the host and cannot be attacked from the host. I said all of this to say, in such a context where you see a value in sort of isolating the SmartNIC, then I don't think those solutions, CXL or CCIX, can bring particular advantages. But again, it depends on what you want to do on your DPU. If you want to use it, obviously, for as a coprocessor to increase the processing power of the CPU, then it's a completely different story. But that's not the way we are going right now.
Gotcha. Nick, what are your thoughts? CXL, C6?
Well, CXL has gotten a lot of traction recently, maybe because of Intel's endorsement of it. The fact that it runs concurrently with PCIe, I think, is also a benefactor for it. And I think it's got more adherence and is moving faster than C6. So I think that it provides quite a bit of capabilities, especially in the fact that it has both the cache version and the MEM version. So it gives it kind of two personalities depending on what kind of a adapter you're going to be in the system. Now, SmartNIC, obviously the cache is important because you want to be able to run a coherent environment with the host and have coherent memory structures that are shared by both the host and the SmartNIC. The .mem, I guess if there's some sort of memory expander that runs through the SmartNIC would also be a powerful capability. So, I'm feeling that CXL has got a lot of momentum behind it, and I think in the end it's probably going to leave C6 behind.
Understood. Michael, what are your thoughts?
I think it's realization that the system, the computing engine is not just the CPU. CPU used to be central processing unit. Now it becomes a computational periphery, and the glass wall on the memory semantics between the CPU and the rest of the board needs to be broken and make them all to be sort of equal citizens in terms of memory semantics, and that's what CXL is doing, basically evolving the coherent interconnect outside the CPU. Now CCIX, it was invented 10 years ago because just to move the ecosystem forward when PCI SIG was slowing down pretty much, and CCIX and CXL are pretty much the same. Doesn't really matter which one takes, as long as we break this glass wall between the CPU memory semantics and all the rest of the system.
Gotcha. Rip, Xilinx has ridden the fence on both of these, buddy.
So I'll give you a cynical answer, and the cynical answer will be, will Intel implement CCIX? And if not, we won't be supporting it. But that's a Rip answer, and it's a cynical answer. A better, kind of more cohesive answer would be, I think there's a place for both in the ecosystem, right? So if you think about it and you look at the design of these things, they're similar, but slightly different. So CCIX is more like of a cache interconnect between accelerators, whereas CXL is more about, can you connect a CPU to a device or to a memory interconnect with lower latency and higher scalability? So they're complementary. A lot of it will also depend on kind of what is your decision matrix, right? Which one are you going to use? So do you need cache coherency? Do you need symmetry between peers, or is a master-slave agreement okay? Do you control both sides of the link? Does it need to work in an x86, or is this going to be an ARM machine or something else? What's the distance you're going to travel? There are lots of things. So I think kind of overall, I think we will see both of these will survive. I think CXL will probably be the dominant in the host, and then on devices and between accelerators on the same chip or on the same die, we'll probably see C6.
Gotcha. Cary, your thoughts?
Sure. First, I was a little surprised by Michael's answer. I think CXL, first of all, CXL is going to be the dominant solution for host-controlled aggregation of resources and coherency there. But I do think it's the CPU is the arbiter of that control, and that's a difference between C6. So I think if you look at solutions where, the CPU or host side is really just one of the players in performing a workload, that something like C6 is needed. Will it be C6? Probably not.
Okay.
But there does need to be coherency between the memory outside of and often not involving a CPU complex, host complex.
Jim, you want to weigh in with final opinion?
Yeah, broadly speaking, agree with Nick's characterization. I mean, CXL looks like a real game changer, and I'm hearing that from customers and partners and end customers everywhere I go. And I've seen a lot of coherent interfaces be not successful and not take off in the market, remain niche-y, let's put it that way. And CXL is one that all signs seem to be pointing positive. And for reasons I guess I don't need to articulate, but it's about the use cases. So the memory, driven by memory expansion, memory pooling, and storage interconnect using memory semantics. These are interesting use cases to drive, broadly speaking, the coherent interconnect off the host. We'll have to see how the standard evolves and whether it can be broadened and will be broadened. I'm not here to speak to that, but I think Intel is the leader of the consortium. I think it has over 150 members now. We really like to work with a broad ecosystem of vendors to finally get a technology like this attached within the industry for the good of the end users. So I will just finally say that I am seeing some killer apps for coherent interconnect with the IPU vision that we're driving in the data center of the future, related to some of the use cases I already talked about, but also through the network port itself and the IPU. And we look forward to bringing those out to the market.
Gotcha. Dan, do we have time for one more question, or you want to wrap it up at this point?
We have plenty of time.
Well, we have plenty of time. Oh, well, in that case, let's go for a security question. Let's see here. Give me 1 second. Okay, so Mario. This one's going to go to Nick. Nick, cloud security has become more important. What security features, and let's try and keep it short, guys. Give me like 2 or 3 security features you expect to see as table stakes in the next generation of smart NICs that should be coming to market in the next year or two.
Thank you. Yeah, I mean, obviously the smart NIC is the gateway to the server, so it could also be the first line of defense or the last line of defense, depending on how you want to look at it. So security in terms of AES encryption, elliptical curve authentication mechanisms, hash, SHA functions. I think those are all table stakes. But the ability to put some sort of firewall functionality into the smart NIC that will, like I said, be that first or last line of defense for the server to be able to do some, looking for anomalies and looking for any kind of threats that may come across, and have some capabilities there. So I think if you kind of broaden security to be just more than just encryption and authentication authentication type of thing, but also to be much more of the shield around the server. I think those are be important capabilities.
Okay, Michael, your thoughts?
Yeah, so yeah, it's encryption and stuff like that. It's obvious. The other thing is that it is not also active protection. Active protection, I mean that you can actually do things like running antivirus on the NIC. You can collect the telemetry data and apply analytics to identify zero-days attacks and things like this. Actually, we announced this type of technologies and solutions recently at NVIDIA. So I think it's basically, you go and run your stuff, all your infrastructure and all your protection on the SmartNIC, and SmartNIC becomes the cluster of data center protection.
Gotcha. Rip, what are your thoughts?
So whatever's been said before, I will agree with. I will add there's another class of security which is becoming increasingly asked about, which is device level security, right? So because a certain class of attacks is moving more towards exploiting microarchitecture bugs, we need to be able to protect ourselves against that. So things like differential power analysis, prevention, side channel attack power analysis, physical and clonable functions. All of these, I think, are important things that we should be thinking about moving forward.
Well, I can strike that question off my list. Cary, your thoughts?
So I'd agree with what everyone said before. I think just to add some twist here, an interesting aspect for security on SmartNICs, because they are in a place where a lot of data is flowing through, is the application of new machine learning and inferencing and analyzing traffic and what's going on outside of the more traditional, just encryption and authentication and DPI approaches.
Okay, Jim?
Yeah, I won't rehash all of that. I do broadly agree. Security is not a differentiator. It's a must-have, and it's not surprisingly just as pervasive across everything that we do at Intel. We preach it every day, and we have very high standards in terms of released products with with security built in and designed in from the get-go, so that the new IPU to go along with our XPU and our CPU is no different in terms of how we approach security holistically, and it really touches upon a lot of the things that were mentioned earlier.
Mario, you get to wrap this one up. Did they miss anything?
Yeah, sure. I mean, as I was saying before, we see the DPU as the element in the security solution, because it is uniquely positioned from the host, because having a network interface, it can be managed through the network. So it doesn't need an agent to the host. It can be completely independent, but at the same time, it can monitor what's happening in the host. And here I like what Michael was saying about having some active means of protection, which can analyze the traffic, but can even analyze what's going on in the host, in the memory, for example, because the SmartNIC is there attached to the bus, to the PCIe bus.
Okay. Let's get one last question in, and this hopefully will help wrap up some of the discussion. And this one's gonna be for Rip. This is your last one, Rip. AMD is coming close to acquiring Xilinx. Intel acquired Altera several years ago for their FPGA architecture. What's the next significant step forward, for this type of computational platform? And for those of you guys that don't have programmable logic in your IPUs, DPUs, whatever, is it something that you might consider adding in the future, or are you good enough with CPUs, GPUs, and that approach? So let's throw that one to Rip first, and then we'll.
So is the question what do you see happening with the acquisition, or?
No, I don't care about what's happening with it.
I meant from a technical level.
Yeah, I'm curious as to where you see the technology going, right? I mean,
okay. Again, my opinion is I expect to see a lot more convergence. I expect to see kind of at both at a hardware and a software level, things being more integrated, more even. I expect to see innovation that spans the whole stack. There is no reason that a company that owns the entire stack from the CPU down to device level couldn't write a compiler that allows you, for example, to offload things where they need to be offloaded and do it in a transparent and easy way. It's a hard technical problem to solve for sure, maybe impossible, it could be argued, but we can get some way there. The other thing I expect to see is, I expect to see, pollination of technology, right? So I'll keep that as broad as I can because I don't want to go into details for various reasons, but there are a lot of, at least on a personal level, I see a lot of things where they're complementary things, and there are technologies, if put together, could do, kind of have network effects. So I expect that we're going to see that sort of thing happening. To be very specific about it, I expect from a SmartNIC perspective that we're going to see different kinds of offloads coming up for various use cases, which may be, more AMD centric. We're going to see various kinds of design parameters change for different workloads. And I'll leave it there on purpose.
Okay. Cary, you guys are hard logic and CPU/GPU CPUs. What's your thoughts?
I think that everyone here would agree that, first of all, let me do the software plug. I think that open platforms and APIs and orchestration and Kubernetes are driving requirements for DPUs. And the number of things you have in your tool chest to go create the right solutions for helping to accelerate it and provide that capability should be robust for every company. So yes, we do CPUs, we do accelerators, we have DSPs, we have Jim's favorite micro-coded engines in some cases. I think having everything in your arsenal is a good place to be in this market because the challenges are so high that you don't want to say, I'm a CPU person, I'm an FPGA person, I'm whatever. So I think you'll see more convergence of different technologies into the same platforms.
Okay. Jim, what are your thoughts?
Yeah, semiconductors is a scale game, and it's becoming, I think, more and more so. So at Intel, this kind of dovetails with everything the themes that I've been coming out with earlier on this panel. And so we think in terms of multiple architectural approaches to the data center of the future: CPU, XPU, IPU. And we also think about architecture types underlying the chips that we have: scalar, vector, matrix, spatial. And we firmly believe that the customers, ultimately the market, will benefit from having suppliers with such scale that can create the right size solutions for them and to solve their various problems, whatever they may be. And I think, having only joined Intel 2 years ago, but been an observer over 30 years, my sense very strongly from the inside is that Intel is quite pleased with the progress. And, we've come 5 years since the Altera acquisition, roughly 4 or 5 years. And the value that the PSG architecture types, the FPGA type that we represent, and the structured ASIC, EASIC, what that represents to Intel at a broader level in multiple touch points than just the initial, MCP with the CPU, right? Mm-hmm. The ways in which our technology dovetails with various Intel technologies from Optane all the way through to CPU is quite impressive. And, I think ultimately we just hope to enable the customers properly and give them what they want.
Gotcha. Mario, where do you guys stand?
Yeah, our platform has is based on processors. I mean, they may be domain-specific processors, but still processors, or then fixed function hardware to get really maximum performance for encryption, compression, functions like that. So right now, we don't see the need, although on our card it is possible to mount a FPGA. We don't use it right now in any use case, but again, my belief is that the perfect solution has different aspects that can handle different parts of the problem. So I would not exclude that at some point we will see also FPGAs being deployed together with the rest of the architecture.
Understood. Nick, you're the last FPGA guy to talk.
Last FPGA guy to talk, and the single one in the crowd here. We are still privately held, so we're in the dating game, let's call it. So no, I think FPGAs can be complementary to. I mean, this was a von Neumann FPGA, kind of bake-off, but in reality, if you're merging the two together, I think it would bring you the best of both worlds, right? Having some FPGA technology that can augment a processor-based and hardware offload, hardware system, I think brings the maximum flexibility. So I think marrying those together, I think brings the customer the most benefit, because you get the flexibility of the FPGA and the hardware, you get the programmability processors, and then you get some of that hardened logic to give you the performance. I think that becomes the ideal solution. So I'll let you go.
Michael, you get the final say, buddy.
Well, Intel did something AMD with Altera, AMD did the same with I'm doing the same with the Xilinx. Good luck.
Good luck. Okay. Okay, Dan, I think that's pretty much it, right?
Well, except that I would like you to try to summarize as much as you can this extremely comprehensive discussion we had of the issue. We talked, I mean, you had 18 excellent questions queued up. And went into them from all the different perspectives, and help us understand kind of what to take away, as specifically as is possible with so much volume of material.
I think if I was to, I mean, I'm trying to bounce, 3 balls in the air at the same time, trying to make this work. But the takeaway that I've got is that neither platform is a clear winner. Obviously, the customer ultimately in the end is going to be the one that wins. And it's really a balancing act between hard logic on the chip for doing things like classification and compression and security and things like that, as well as having a good solid programmable interface, whether that's an ARM interface or an x86 off to the side, or programmable logic. I really think there's a place for all of these things in various areas, given the amount of content that's out there, the amount of programming that's out there. And some of these things are very complex to do. I mean, some of the OVS overlays and things like that, may not be easily solved, with simple logic. So it's, I think it really is a mix of everything.
Well, you had 6 panelists have no trouble coming up with 3 functions that had to be in the chip, on chip functions,
right?
Which says that you're going to need some dedicated processing in most of these environments, because where are the environments where you don't need some of these functions? But I think as we're seeing such varied workloads coming out now from sensors and IoT and autonomous stuff and machine learning applied to all kinds of things we wouldn't have expected 4 years ago, you're going to need flexibility in the programmability of those things as well. So I think that argues for having programmable logic pretty widely deployed also. Now, I don't know that the panel has come to conclusions about where you're going to see the greatest leverage from this stuff, whether it's going to be in the data center, or it's going to be at the provider edge, or it's going to be in the universal CPE. And I kind of like your thoughts, Scott, on where you see the growth for this sort of hybrid market.
That's a good question. The growth, we have the hyperscalers obviously are driving a lot of the SmartNIC demand, but some of them are doing their stuff on their own, right? Because they obviously don't want to be beholden to any one vendor. They'd rather just do it. It's the second tier ones and some of the other foreign hyperscalers that will go with off-the-shelf solutions. And as we heard, Jim mentioned, Intel's had some good wins. NVIDIA clearly has had some huge wins, as have Pensando and some of our partners on the panel. I think really at the end of the day, the market is going to decide which approach wins out. VMware's Monterey may be one of the things that tips the scales on that, but it's literally just starting to dribble into the market in the last week or so with some technology preview stuff. So we don't really understand yet if that's going to make a big difference or not. I still think it's anyone's game to win. It all depends right now on execution, right? Everybody getting their latest and greatest stuff out to market and providing it with the right software programmability and features and functions that meet the needs of the customers. So
you touched on a sensitive issue, which is the role for independent vendors, given how much the hyperscalers are building themselves.
Right. Yeah. Google and Amazon, they're kind of off the table, right? So that leaves, everybody else that's under that, Microsoft and, Baidu, Alibaba, Tencent, all of them. And then the second tier guys that, we're not even going to go out there and try and name, because there are a dozen or more of them. And I think that's what everybody's chasing after is those. So I think that's it.
Well, thank you, Scott. Thank you, all the panelists. I mean, you prepared well. Scott, you prepared immensely well. And we could wrestle with this for the rest of the day, and maybe again in a year. But I think what my conclusion is, the conclusion I draw here is that we are pushing the envelope in both of these technologies, both the von Neumann and the FPGA directions, which is great to see. And we need them both. And it could be that the marriage of Altera and Intel and AMD and Xilinx, if it happens, will foster some greater integration of these in some kind of a cogent manner that gives us better performance, lower power, and more flexibility in addressing the workload needs. So I'm looking forward to seeing where it goes from here.
Yeah, and I didn't even push on the power button today. I mean, that's an issue for everybody at the table here. Is how do we get under 75 watts or stay under 75 watts, which is not really an issue. I mean, we all have to go to optional power.
It was mentioned today at some point. I don't remember what session or talk it was in, but it's an issue there for sure. Yeah. So anyway, thank you all, and we look forward to having you continue to participate in Hot Eye this week, and look forward to the questions you put on other people's Slack channels to ask them, and to continually give us your feedback. So I'll declare this the end of the panel, and right now I would like to introduce the Head Bubba Memorial Cocktail